Third up, Robin Cockett from the University of Cambridge, fellow Canadian. I'm going to stand over here. I'm a Canadian.
Sorry.
The first time I met him, about 40 years. Oh, I'm sorry. Thanks. Can you help me with this? Can you not hear me?
No, they can hear you, but it's for the Zoom.
Oh, for the Zoom people. Ah, that's pretty important. Yeah, just stick it. Oh, stick it in.
Yeah.
Okay. Should I start again? No. No. Okay. So the history of Phil Scott. The first time I met him was about 40 years ago at a conference, and he discovered I came from I'd done my PhD at the University of Leeds, and he said, "Oh, I was born there." So I thought I had a very special connection to him, but then I discovered that actually when he was 1 year old, he moved to North Carolina. So he had absolutely no memory of Leeds. But anyway, then he did his undergraduate degree in Chapel Hill, his PhD in Waterloo, and he worked with Dennis Higgs. And I don't know, Dennis Higgs was an interesting guy. He had a job in South Africa. He didn't like apartheid and demonstrated and ended up in jail. And that's how Canada got Dennis Higgs. Anyway, then he did a postdoc at McGill, and that's under Jim Lambeck. And of course, that's what resulted in a lifelong collaboration. And was a major influence on Phil. And then in 1982, he joined the mathematics department in Ottawa. And he was there till he died, and he was active till he died. You probably know that he actually had prostate cancer, a rare form of prostate cancer. And he contacted me because he knew that I'd had prostate cancer, and asked me for advice. And I said, "Phil, treat it like any mathematical problem." And as a result, he contacted every mathematician he knew, and especially those who had prostate cancer, and discussed it with him. Which maybe wasn't such a great idea. So Phil had a major influence on Canadian mathematics. He was on the NSERC panels, and he heavily supported categorical logic, and would sell the categorists in Canada to the NSERC panels, so that we actually got some funding, which was very good news. So I'm going to run through, he actually wrote up his own output, and so I'm just parroting it here. But one of the things that's remarkable about Phil is he, if there was a new subject of interest, like linear logic, he was right on it. But also you'll notice in between the linear logic, there's this feasible mathematics. There's a lot of Lambeck influence in what he did. And of course, the book that he wrote, we'll come back to that, The Introduction to Higher Order Categorical Logic. Notice the early work that he did, which was in intuitionistic type theory with a free topos. And that was actually a major influence leading to the Lambeck and Scott book. But he also had some great survey articles on linear logic, and in particular with Rick Blut. And a lot of work in theoretical computer science, and that's how he got onto the NSERC panels and was able to support the theoretical computer scientists, including category theorists. I'm not going to comment on all of this because some of it you'll know, the geometry of interaction. So you've just heard about quantum computing. He did some work in quantum computing. Yes, Mark's going to talk about the MV algebras shortly that he worked on. But he also had an interest in recursion theory. And in particular, one of the last papers that he wrote was on aspects of categorical recursion theory with Peter Hofstra, who you know also recently passed away. And some stuff on categorical logic. Okay, so you've seen this picture, but what's the important thing about this picture? Well, it's the Tilly hat.
Yes.
So this is a mark of a Canadian mathematician. We all wore Tilly hats. And, and there he is in the Tilly hat. Okay, so the book that changed everything. I mean, this really did have a huge effect on the community. Rick mentioned this, that all the young graduate students were reading it at that time. So from the introduction, there's a little acknowledgement, and that thanks Marcia Rodriguez, who is his wife, for the bibliography. And I think it's important to realize the importance of wives, of support people, partners to mathematicians. And Marcia certainly supported Phil. Whoops. Okay, so again, from the introduction of his book, I'm just start at the beginning and going forwards. They do apologize for an undue emphasis on category theory. Because at the time, category theory, well, was not totally popular with mathematicians. He also had this strange comment: we decry the overzealous application of Occam's razor. Now, less surprisingly, we believe that type theory is the proper foundation of mathematics. And in particular, of course, of the free topos, which with the natural number object. And indeed, the second half of the book is really about the type theory of topoi. However, I think the first half of the book was much more influential. And so I'm going to talk a little bit about that. But before I do that, of course, I said that category theory wasn't very popular, and category theory wasn't popular because it was making outrageous claims. And the categorical imperative, I think that's an Arbim Manez slogan, category theory is the mathematics of mathematics. If anyone knows where that came from, I'd be interested. But a rather important slogan was Jim Lambeck's slogan. And in fact, this captured, I think, a major revolution, really, in mathematics. Because set theory was all about what things are. They eventually are sets with structures, right? But what category theory did is it turned that on its tail and said, well, the only important thing is how things interact. And I think Lambeck and Scott's book just came at that moment where that transition was happening. And of course, Jim caught it, which just in one sentence, which was amazing. Talking about slogans, another peculiar thing about the book is it numbered the slogans. and
Roman numerals.
And Roman numerals, that's right. So I guess it wasn't the same status as theorems. But I love slogan 4, that many important concepts of mathematics arise as adjoints left or right to previously known functors. And of course, the last one that I've got here, many categories are Eilenberg-Moore categories of familiar categories. Okay, so back to Occam's razor. We decry the overzealous application of Occam's razor. So what was all this about? And in fact, I found this a little bit peculiar about, well, we'll get to it. We'll get to it. Okay, so Arthur Conan Doyle's version of it was that, well, you're probably all familiar with this, but this is not what he meant. Here is William of Occam. He was a 14th century, monk, I guess. The monks were the educated ones. And actually, interestingly, I discovered he was actually a student at Oxford from 1309 to 1321. His title that he obtained from Oxford was Venerable Beginner, which, well, he was here for 11 years, and he got into trouble with the Chancellor. And it wasn't because he was so slow in graduating, but it was because of his views. And one of the views was he espoused the separation of church and state. And that put him in conflict, not only with the Chancellor, but also with the Pope at that time, and who was the Avignon Pope, I should say. And he had to go to Avignon. He tried unsuccessfully to defend his views and actually had to flee from Avignon. Here's Occam's razor. It's the principle of parsimony. Entities must not be multiplied beyond necessity. Oops. Oh no! What happened there? Oh no! Is there that's Occam's razor. It's... I don't know what the hell it did. Was it me? Ah, wait. You can have my talk all over again. Okay. That wasn't even my slide. It was. Well, maybe I should end.
Sorry, that's the right one. I don't know what the hell happened there.
How could I have?
I'm just going to stop.
Oh no, did it not copy across successfully?
No. Could you not do that again? Whatever it was you did.
I just pressed the next slide button.
You press the button that's only designed to work on Windows. Okay.
Oh yes, well we've gone on. Yeah, I'm going to have to go back a little bit.
You've got 10 minutes.
Oh, okay, thank you. Well, okay. Let me just quickly. So they give an example that when you have a Cartesian closed category, what you can do is, because the product structure is actually determined by the implication structure, because there's a little adjoint there, you can actually construct the whole thing around the exponential. And anyway, here's the point that they were trying to make is that right, the order in which things have happened has all changed. So I'm struggling a little bit. So the point was, and this was due to Gensen, was he realized that it's much more natural if you retain some of the conjunctions and connectives as primitive, rather than getting rid of them. So, I mean, you know, it's well known you can get right down to the Sheffer stroke, but the trouble is the identities then become meaningless. And Levier also proselytized this in category theory. Okay, so the point is, using Occam's razor actually gives you usually an interesting thing, and it's well worth trying it out. But the point is, you shouldn't lose the connection with all the connectives which are around. And so, having decried it, one of the things that they did was to apply it, and they applied it to look at categories with only one object. No. Oh, good. Okay. So, and they asked, well, what is a Cartesian category with only one object? Now, you can't have a Cartesian object with a final object because that would kill everything. So they just wanted binary products. And it's what they called a Cartesian monoid. And you can express it just satisfying these three identities. And that gives you a little category where X is actually the same object as X cross X. And you can prove the uniqueness of that arrow just in a very standard way, which I think most of you are very familiar with. So it's important to realize that that one identity C3, if I go back, will I? Yeah, which I've got there as the first move, can be broken down into two things: the surjective pairing and the distributivity of the pairing, and they're equivalent. Okay, so if you want to form a Cartesian closed category with one object, what does that look like? Well, what you have to add is an operation, a unary operation called currying, and eval, and that gets what Lambic and Scott called a C-monoid. And here's the uniqueness of the currying. Whoops. Okay, and so there's a famous result of Dennis-Cott that if you split the idempotence of a C-monoid, you get a Cartesian closed category. And indeed, any Cartesian closed category with an object which is isomorphic to its product and its exponential gives on that one single object the structure of a C-monoid. And the one thing you have to worry about is where the final object comes from. But when you split the idempotence, all you have to show is that there's an absorptive element, and that gives a final object. And of course, what you do is you take the curry of the second projection, and that gives you an absorptive element. What's interesting is that this doesn't actually give you a general model of the type lambda calculus. And so I chased Phil Scott down and asked him, well, why didn't you produce a general model? And Phil pointed me to an exercise, which I thought, I mean, why hide these things in exercises? But anyway, that's what they did. And I think it was a great pity because they were almost there. And so the general model comes from a weak Cartesian monoid with weak exponentials, where what you do is you use the distributivity over the pairing, and you drop the surjective pairing axiom. And that gives you when you split the idempotents, what Peter Hofstra called a latent product. And but of course, you don't have a final object. Now, what's a little bit interesting about this is you now have a system where there's a rewriting system on the products. Okay, so a weak C monoid, you add back in the currying and the evaluation, but you modify the second rule to make it weak. And then, well, there are some little observations that you have that curry eval becomes an idempotent. And when you apply the curry to F and then the idempotent, this actually is invariant. The curry F is invariant under that. And in that sense, you're giving a code, but it's a canonical code for these things. And of course, this was, then you get the general model, and you get the Scott-Koymans theorem, which is that any Cartesian closed category with an object U, such that the product is a retract of U and the exponential is a retract of U, then end U is a weak C monoid. So it was a pity, I think, that they didn't actually push that bit through in their book. But you can go further, and that sort of connects with what Sampson was saying, to look at this from the point of view of combinatory algebra. And you can get a little combinatory monoid out by taking a Cartesian monoid with an application and absorbing elements K and S, which satisfy, well, the combinatory algebra identities. And of course, Schoenfinkel discovered this functional completeness property. And this allows you to simulate the lambda binder. However, there's something important to realize, that if T1 and T2 are equal, it doesn't follow that when you lambda abstract that T1 and T2 are equal anymore. So it's a much weaker non-canonical lambda calculus that you get out. And this is what Peter Hofstra and I called a total Turing category. I mean, the total maybe should be in brackets, but a Turing category. And the point is, you can axiomatize this by saying that the T, the object T, the Turing object, acts as a weak exponential for every other pair of objects. And that gives you then that T is actually a combinatory monoid sitting inside your category. And if you split the idempotents, you get a big category. Right. So in fact, total Turing categories were first written up by Longo and Moji in 1990. And it wasn't until, well, many years later that I got together with Peter Hofstra to talk about Turing categories. And what we added was the partiality. So actually, Turing categories correspond to partial combinatory algebras, but living somewhere. And then Turing categories occur everywhere. So what you can do is you can sort of add to your basic Turing structure some other structure. So in particular, the differential lambda calculus by Erhardt and Renier is actually an example of a differential Turing category. And in fact, my student, Jonathan Gallagher, and I wrote this up as to how you regard this as a little one-object category sitting in a Cartesian differential category. So another sort of interesting direction for Turing categories, which is the partiality is important here, is the idea of trying to amalgamate to under one hat complexity theory and computability. And so they both form Turing categories. And for instance, you can have a Turing category with a Turing object where all the functions are polynomial time. And in fact, you can push this right down to, I think it's linear time to get these Turing categories going, so that you can re-express complexity ideas in Turing categories. And in that sense, I think Turing categories are abstract computability, and there's a way of amalgamating complexity and computability. Okay, well, I hope you can see this. It's rather dark, but Phil liked Oxford, but his true love was Edinburgh. And this is a photograph of Thanksgiving in Edinburgh, taken by my wife. And actually you can see, maybe you can't see, but Marsha is sitting in the background. Phil is sitting to the right, and I'm sitting next to Phil. And it's a typical dark Edinburgh night. Okay. Well, thank you very much. That's. And oh yes.
Yes, Alex.
Yes, you mentioned the first half of Phil's book is better known than the second half. I'm not sure I agree with you about that, but what about the third half? You didn't mention the third half at all.
Oh, the third half. Okay, yeah. It depends on how you count.
But there were three parts.
I think the first part was just an introduction to category theory. The second part was to the lambda calculus, and the third part was toposes. Is that not right? The other part.
There was another part.
What was the other part? Go on.
About that computability, yeah. Natural numbers objects and things like that.
Ah, yes. I was going to mention this, right? And so Phil was very interested in the representability of various functions in toposes and the lambda calculus. And so you're right to bring this up, right? Yeah, but you had to read it. I also should have mentioned, of course, the importance of the book to this community was because of the Lambeck, Curry, Howard isomorphism, which essentially the book exposed this in detail for the first time. What does the blah 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 mean?
Thank you very much.
Okay.